All right, so we left off on Thursday with this because we didn't have very many people here Friday due to prom. But the first thing that I want to talk about is how you can calculate all of these things. So consider the reaction of two sulfur dioxides and oxygen gas forming two sulfur trioxides, and it says calculate delta H, delta S, and delta G. So to calculate these two, what did you have to do? You had to use Hess's law. So I am going to need your help. I'm just going to rewrite it like this. So I've got two SO2s plus O2 yields two SO3s. And so the delta H of the reaction is equal to the sum of the delta H of the products minus the sum of the delta H of the reactants. So when I do that, I'm going to have the product, which is 2 times SO3 minus. Now, this next part, there's something interesting about the tables, and I want to go back in and look at it for just a second. It has to do with this part right here. Okay, so my question is it possible for a compound to have a 0 for delta H? Is it possible for a compound to have a 0 for delta S? No. Is it? Well, it is, but will you ever see it? No. Is it possible for a compound to have a delta G that is 0? Yes. Okay, and we'll kind of talk about that. And so I just wanted to point that out as we went through this. And so when you calculated this, you know that you could have left in the delta H version, you could have left O2 out. And so that was just left with this. Now, the easy part was plugging in the numbers. The hard part may have been the calculation. But when you did this, what was the final answer, number-wise, for delta H? That says 198, isn't it? All right, so negative 198. Now, that's just a number. Let me key you in on something. Anytime they ever give you this stuff, if you will go back and you will actually look at the table, the units are given in the table. So what is the delta H unit? Kilojoules per mole of reaction. Okay? Now, so that is all for delta H. Delta S is a little similar, but this time it's going to be 2 SO3 minus 2 SO2 plus O2. You've got to kick in that O2 value. So it was almost the same math, but again, it was a little bit different on the other side. So what was the final answer to this one? What was the number? Okay, so negative 187. And I've been kind of cluing you in on this as we've been working this stuff, and I'm telling you now on the test, there are going to be some problems where you actually have to change some units, okay? Because if you notice, right here it says kilojoules, but right here it says joules. So for right now, it's okay if we leave it as 187 joules per mole, right? Joules per mole. So we've got H and we've got S. Now, how do we get it to G? What formula is that? Ghetto homies take speed. Okay? So delta G equals delta H minus T delta S. So we know that delta H was negative 198. Now, if you go back and you look at it, it was 198 kilojoules. Well, how should you rewrite this? Perfectly fine. You can convert the other one to kilojoules. I personally like converting back to the original unit. It does not matter how you do it at all. Minus, and in the problem, I think it says right here, I noticed several of you leaving this as 25. But again, if you make your units match, what do you notice about the unit right there? There's a Kelvin. So what is 25 to Kelvin? 298, thank you. So I've got 298 times the delta S, which was, what was it, negative 180 something? 180, and I forgot the Kelvin here. So 187 joules per mole. unit-wise, what's that going to get rid of? It's going to get rid of your Kelvin. And all it's going to leave you left with is joules per mole of reaction. And when you finally multiplied and subtracted this off, what was your final answer? Give me joules. Is that right? Yep, very good, sir. Okay, negative 142,000 joules per mole of reaction. Okay with this? In fact, I would have left it as negative 142 kilojoules is how I would have put it. That's what I would have done. Either they're the exact same answer. Now, the more desired is kilojoules. Now, I'm going to take this one step farther, and this is something we did not do yesterday. I'm going to add a part C and a part D to this. Part C, simple question. Is the following reaction thermodynamically favorable, yes or no, and please explain your answer. That's all you have to write. No, not exothermic. It is thermodynamically favorable because delta G is negative. Now, here's the next part that I'm going to get you on. And I'm just going to label this as part E. At 25 degrees Kelvin. Oh, wow, that was bad. My bad. That's wrong. Yeah, it is. I meant Celsius. How you've got, all of a sudden, we're talking about all this thermo stuff, and then they just drop the equilibrium thing in there. How in the world do you go from a equilibrium, or from a thermo constant to an equilibrium constant? What? Rat link. So that's what the Harvard fish is for, right? Okay. If you would look at this, and I'm telling you, on the matter of fact, on this part, which you'll actually get, look at that bottom left box right there, Jacob. Do you know what is the title of that bottom left box? Okay, so we know we're got to do a thermo. There's also an equilibrium part. Is there anywhere in there that has a K connected to it? What is it? So that's the thing that I need you guys to understand. So negative rat link. Okay. Now, calculate K. I really want you to do this. You just told me that you just solved for delta G. I want you to set everything up, get all your units in the right place, and see if you can calculate. I'm telling you right now, you're going to have to do this on the test. So I'm giving you an example of a test question. This, like, that whole problem will be one free response question. Pretty much. I mean, there's a few other things. Yeah, there's a few other things. You tell me. All right, I'm going to kind of start this process, and all I'm going to do is I'm going to get K by itself first. So what's the first thing I got to do? The ln of K is equal to delta G over negative RT. That's where you got to start first of all. Then to isolate K, this is the reason I wanted to show you this. You can't just divide by natural log. What do you have to do? You take the inverse of it, which is E to delta G over negative RT. Now, here's the deal. I'm going to start with the easy numbers first. Do y'all know what three triangles mean? Therefore. So, E. Now, I'm going to start with the bottom numbers. I'm going to start with a constant. R. Now, which R? Gas R or energy R? Y energy. We're dealing with delta G. Okay? All right. So, it's negative. Excuse me. It's 8.31 joules per mole. Now, since our R is in mole, What does the temperature unit have to be in? It also has to be in Kelvin. Now, why did I write this up here? That's one reason. And number two, that I create consistency throughout the problem. Yes, because if you change the temperature, would it change the equilibrium constant? Absolutely. And you would have to do a whole different calculation, which I've never taught you how to do, to find that. So you'll see consistency throughout all this stuff. So 298 Kelvin. Now, here's the next weird part about this. Which delta G are you going to be plugging in? The big one or the small one? Why the big one? Because I need it in joules. Why does it have to be in joules? The R is in joules. Okay? Which I wouldn't do because it's a constant. Leave it alone. So it's negative 142,000 joules per mole of reaction. So now, let's start with what we do know in terms of units. What do we want the unit on K to be? Nothing. We don't want a unit on K. And so if we look at our units, what's going to happen to your joules? They cancel. What's going to happen to your kelvins? They cancel. And your moles. They cancel, so you're left with nothing. That's why I need you to see the unit aspect of this as well. I could care less what the numbers are. The units are what's going to get you to the answer. Now, this is the hard part why I wanted you to do it in your calculator. Because here's what we've got to do. There's several different ways. If you've got the 89, you can plug all of it in at once. Here's what I would personally do. I would take negative 142,000 and I would divide it by, close my parentheses, time 8.31 times 298, close my parentheses, and get a number. Okay, that's what I would do. Then I'm going to hit second ln and get this thing. Now, if you're on my big one, you can just go up and grab it, pull it back down. But on this, you have to hit second answer, close my parentheses, and that should be your answer. You got. Now, did y'all round and put the replug the numbers back in, or did y'all put the whole thing in? Is that what you got? That's fine. 8.31. Oh, okay. That's the difference. And y'all copied it right off the formula sheet. That's perfectly fine. It's the biggest deal is it times 10 to the 24th. That's the important part. That's the important part. So it's 8 or 7 point something times 10 to the 24th power. Now, how did I know before I ever began this question that the answer had to be greater than 1? Delta G was negative. Very good. Be okay with that? Be all good and grand and spectacular. All right. What if there was... do I need to show any of this, anything else? Okay. The last part, and you'll never see this, but I'm just throwing everything at you. Look at your formula sheet. We've been talking about delta G and K and H and S, and all of a sudden they throw an E in. The green. How in the world is still under the Thermo one? How in the world do you go from Thermo to cell potential? Say it again, Mitchell. Now, this is the only way you can go from G or K or anything to E. Now, they've given you nothing about cell potential, no voltage, no half reactions, no redox part of it. And all of a sudden they said, how much power could you get out of this? Well, if you've got all this energy to do some work, you should be able to get some voltage. See if you can calculate some voltage. This one's much easier than the last one. No, not the state of matter. What's its oxidation state? It's 0. Here it's -2, right? So what process is that? This is reduction. So this is red cat. right? All right. So see, you can't do it with this one. So never mind on that. However, it was a good attempt. I just wasn't thinking about the reaction. But if you do have to go from G to E, you have to use negative in fact. Yes, that part will be on it, but it will actually be a legitimate reaction that you could actually calculate it with. Okay. What are the units for Faraday? Coulombs per mole of reaction. Okay. All right. So again, for a constant temperature process, which means basically we're going to keep it the same temperature, all this stuff must be true. You already know every bit of this. Now, this next part, this is kind of funky. I've never really liked talking about this, but I think sometimes just showing you things in different ways. Here's the first thing I need you to understand. This line right here is 0. Heck. That purple line is 0. So, what do you notice about delta H in this reaction? It's what sign? Negative. So what type of reaction are we dealing with? We're dealing with exothermic reactions. Okay? Now, what is happening to the entropy? It's increasing. Would you all agree that entropy and temperature have to be related directly? Why? The more energy you have, the more dispersal you're going to have, right? And so as your as your T delta S is increasing, your delta H is doing what? As your T delta S is going up, what is happening to your delta H? It's staying the same. However, what is the value of delta G doing? It's becoming more negative. It's getting larger and larger and larger. Does that make sense why? Let me ask you something. What does nature prefer, negative delta S or positive delta S? Okay. Ignore what I just said. What does nature prefer, a positive delta H or negative delta H? Negative. Is it negative? What does nature prefer, a positive delta S or negative delta S? Positive. So are both of these what nature prefers? So what is G going to be? Negative. So the more and more energy it releases, first of all, as we move this way, what is happening to the value of our energy being released? It's getting, because it's moving along the x-axis, right? Yes, no? It's releasing more and more and more and more energy. And so delta G is becoming greater and greater and greater. So both delta H and T delta S terms will be negative, so delta G will be negative regardless of the temperature. So it's spontaneous at all times. Now, have I given y'all this out yet? All right, this is going to really help. So let me give y'all this. So basically everything you're fixing to see is going to... All right, so here is what we got going on. If this were a 4-point plane, what is in quadrant 1? Nick? Positive, positive. Okay? All right, what about quadrant 2? Negative, positive. What'd you say? I have no clue what you're talking about. We're not talking about that kind of stuff. All right. What about quadrant 3? All right. And then quadrant 4. So let me ask you something. Which quadrant does nature really want to be sitting in? Top right, top left, bottom right, bottom left. It is kind of a winky face. That's why it's winking at you. That's what nature wants. It's winking at you. Hey, come on. No. Which one of these does nature absolutely despise? No, it doesn't. Because you're talking about two different independent variables. You're talking about entropy. Yeah. Stop. Yeah. Uh-huh. No, it's not. Oh, my bad. I'm sorry. I just did the colors. Is that why it's weird? I just did the colors, not the signs. My bad. It's right, because it is X and Y, isn't it? Wow, I fudged that. All right. Guys, y'all. Nick, stop. So here's the deal. Regardless of, I did mess these up. Oh, I did do that wrong, didn't I? So I need to, hang on. You did, but I was thinking, I did YX instead of XY. All right. So this is negative, negative, positive, positive. Now it's positive, positive. It did change it. Negative, negative. So now let's redo this. And this was my fault. I'll take the blame. That's much better. All right. So that's what's going on. So nature always wants to be in that top left-hand quadrant, because when you have delta S that's positive and delta H is negative, it'll always be thermodynamically favorable. But here's the situation that you guys are going to run into. You're going to run into this, and you're going to run into this. And so there's an easy way to remember when it will be a specific, if delta G will be positive or negative. This part right here, and I think it actually has it written. If it doesn't, you may want to write it in. This is going to be spontaneous. This is going to be TF at high temps. Now, what's an easy way to remember that? What are both of those signs? Positive, two high things. Okay. What about this down here? This is going to be TF at low temps. Okay. So again, if you run into something, here's the part that always becomes difficult, is what temperature defines high temperatures and what temperature defines low temperatures. It depends upon the reaction, and that's what I'm fixing to kind of show you over these next few slides. And I think this little sheet of paper may kind of help you out in trying to determine when it's spontaneous and when it's non-spontaneous. So what happens when you look at this? Notice what happens at this point right here, where this purple X is. T delta S crosses delta H. Do you agree? And at that temperature, what happens to the reaction? It's no longer spontaneous. Okay? And so really what happens is there's a specific value that the T delta S will cross that delta H line when it will no longer become spontaneous. Because first of all, is delta H positive or negative? Again, here's your zero. Is delta H positive or negative here? It's negative. What's happening to delta S? Is it becoming positive or negative? It's becoming negative. Okay? Which nature doesn't like. So it's only spontaneous at low temperatures. So if the reaction is sufficiently exothermic, it can force delta G's negative only at temperatures below. And so that's, like I said, I've never really used this, but some people see it in a totally different manner. Same concept here. It's not spontaneous until a certain temperature is reached, because there's so much exothermicity that the energy is going to drive the reaction forward. And then here's the case. Delta H is positive, delta S is negative. So both delta H and delta S are working against it. This kind of process will not proceed spontaneously at any temperature, so it doesn't matter. So that's what that little graph is going to kind of help you guys with if you need to figure it out. All right. Let's see. Skip all that. Skip all this. Skip all that. We've seen this. Guys, in a weird, strange kind of way, this is just like Nernst, but it's with G. And I've never seen a problem including this. I honestly kind of need to take it out. But, no. Here's what this is. Basically, this is trying to determine delta G at equilibrium, or equilibrium, constant equilibrium. We know that delta G is 0, Q is equal to K, and so you can plug all these things. So this is where negative Ratlink comes from. So this is just kind of the derivation of Ratlink. All right, somebody help me out. Read that first sentence up there. All right, so the key part about this one, we've already seen this. At the blue line, down here at the very bottom, what point are you currently at the blue line? What is the slope of that line? 0. Well, what do we know about delta G at equilibrium? That's why. So you can determine the value of delta G by the slope of the line. And again, this is graphical interpretation. This is a very in-depth kind of thought process that's going on here. But you don't have to. We're not going to get into the depths of it. If you want to read through this is fine. I actually went through a training on all this. The guy kind of talked about how this is how delta G is really determined, and it went right over my head. But I tried to sit down and I tried to make it sound reasonable. So if you want to kind of read, if you want to go through this, it's perfectly fine. But I don't want to spend a whole lot of time because, I mean, like I said, it gets really in depth about how all this stuff works. We got a few more things I want to go through. So like I said, it's there for you if you really want to understand it, but I don't want to take the time to do it. All right. So this is what I want to do. I want to spend the next little while going through these types of problems. So I think this is on the back end of your stuff. So what I want you to do is I want you to do A, B, and C, and we'll talk about the answer, and then we'll come back and we'll do D and E. So do A, B, and C. I don't think there's any math in that. It's more of verbal cues of how you need to answer this question. All right. So predict the sign of the entropy change as the reaction proceeds to the right. Explain your prediction. So is it going to be positive S or negative S? Why negative? Very good. You're going from 2 moles of a gas to 1 mole of a solid, creating more order in the system. Okay, so that's negative. B, if the reaction spontaneously proceeds to the right, predict the sign of the enthalpy change, delta H. Explain your prediction. Why negative? Very good. That's the key word. So spontaneously proceeds means it's an exothermic reaction. Also, what type of reaction is it? It's a formation or synthesis reaction. And anytime bonds are formed, energy is released. All right. The direction in which the reaction spontaneously proceeds changes as the temperature is increased above a specific temperature. Explain. The direction in which the reaction spontaneously proceeds changes. Oh, and here's why. You just told me if B, because it's exothermic, right? Well, as the temperature increases, according to Le Chatelier, what side of the reaction are we affecting? We're affecting the products. So as the temperature gets higher, what's going to happen to the shift of the equilibrium? The equilibrium will be altered to return to the products, the reactant side. No. All right, so here's B. Because a mixture of two gases produces simple pure solid, extremely large decrease in entropy, so it's negative. In order for spontaneous change to occur to the right direction, the enthalpy change must overcome the entropy changes, favors the reactants. So it's exothermic. All right, this one, delta G is delta H minus C delta S. The reaction will change direction when the sign of delta G changes. Hence, delta H is negative and delta S is negative. Then at low temperatures, the sign of delta G is negative and spontaneous to the right. At some higher temperature, delta H is equal to T delta S and delta G is 0. Therefore, at any temperature higher, we'll see delta G as positive and spontaneous in the left direction. So here's how I want you to answer this. When this becomes more positive than delta H. Yep. Exactly. So Claire, what you were saying kind of is right. That little sheet. So it's spontaneous because both H and S are negative, and that's only spontaneous at low temperatures. So once the temperature bypasses the delta H, it will then force the reaction the other way. It'll become non-spontaneous. Hang on just 1 second. Let me go back and look at something real fast. What is the... Okay, here's why D does make sense now that I've read it. What is the value of the equilibrium constant at the temperature referred to in C? That is the specific temperature at which the direction of the spontaneous reaction changes. So, when delta H is equal to T delta S, that means delta G is 0. So, if you look at it from this perspective, what would E, then what is K? Delta G is equal to 0 to K is equal to 1. So, it'd be at equilibrium. That's a bad question. Now, this last one, if more of this product is added to the system at equilibrium, what would happen to the value of delta G? So you're adding solids, so what's going to happen to equilibrium? I don't even know what this says. I don't like that question either. All right, so we'll pick up here tomorrow. Yes. No, solid and gases don't matter at all, but you need to state how many moles of each it's utilizing. Even that, because gas to solid is the key, but just tell me how many of each. No, but let me ask you this: what if they said of two reactions, which one is more disorder? Is it 2 moles of a gas to a solid, or 1 mole of a gas to a solid? 2 to 1, and that's why you need to just kind of mention how many is going to, because the more of one thing into the complete opposite change you're going makes it even more disorder.